So I guess I'll continue to specifically welcome Carl Greenbaum, who is the first speaker. He is the Associate Technical Director for Surveillance and Intelligence Division of the Mitre Corporation, Group Leader for System Engineering Division at Grumman Aerospace, and he has done a lot of activities in Moon and Mars science and technology recently. And with that, today we'll talk about microwaving regolith for dust and radiation protection and resource acquisition. So please, Carl, go ahead, and the floor, the air and the ether is yours.
Thank you. Yeah, as Nicholas mentioned, part of my background was working on the Lunar module program back in the late 60s, and I'm still a space geek. So talk about microwaving regolith as a means to solve some of the many challenges of lunar settlement. Okay, can everybody see my title slide? Can anyone see my title slide? Okay,
I can see it. It's blank.
It's blank?
It's blank.
Yes.
So it's a blank slide.
Oh,
It just says presentation 1. You probably need to just bring up your presentation.
that better?
Nope, still the same one.
Try sharing. I mean, you maybe are sharing the wrong window, so try sharing again.
Yeah, go ahead and stop sharing. Yeah, I can kill your sharing. And then when you go back to share screen, just see if the other window is up.
Yep.
Yeah, that looks right.
Except it's all the full set of slides. But yeah.
You just need to go to slideshow.
Yeah, I did.
The tab 2 to the left from view. And there you go. All right, looking good.
Okay, sorry about that. So, as I mentioned, I spent some time working on the Lunar module program, and subsequently, more recently, gotten involved in some research and studies of various things. I even participated in the moon-based design contest that the Moon Society sponsored a couple of years ago. So, as numerous problems to be solved listed here, dust-related, mechanical, and respiratory problems are among the most serious. As I mentioned yesterday, I'm with John Young, who came back from Apollo 16 and said that dust is the biggest problem to be solved, for a return to the moon. Obviously, surface radiation and the other items listed there are also significant challenges. Now, when Jack Schmitt and Gene Cernan were on the lunar surface in Apollo 17, well, you can see what Gene Cernan had to say. He was just filthy. That's him on the right. Schmitt, on the other hand, seemed to enjoy wallowing in the lunar regolith. And he was, you can see that's Jack on the left, and he was just filthy all the time. It did pose numerous challenges to the the equipment, the wrist seals and the helmet seals on the suits, as well as obviously that's Gene Cernan. His undergarment is filthy. So obviously we need to do something about the dust. Now, an important contributor to dust mitigation, I believe, is sintering the pathways and roadways that we're going to be using on the lunar surface in the area around the settlement. There have been talk about using solar energy, which is fine, except that you only have the sun half the time. And I believe that there's a lot of promise in using microwave energy to sinter the surface. That is, you almost melt the top layer of a few centimeters, which gives you a surface that you can traverse without raising a lot of dust. Equipping system with a high power transmitter with a high gain antenna, should do that. As you mentioned, we'll mention later, there are these nanophase iron particles in the regolith that enhance the coupling and make it more effective, and it's difficult to evaluate that with simulants because that same characteristic is not present. Some studies have suggested that 5 to 10 gigahertz frequency range will concentrate the microwave energy in the upper shallow layers, which is where you want it for sintering. And to the best of my knowledge, there's only been one experiment that used actual Apollo regolith to try to melt it. And Dr. Lawrence Taylor put 80 grams of it into his microwave and just said that it melted almost as fast as your tea water is heated. I hope he didn't get it mixed up with his tea. The mechanism to do this sintering, this is the NASA prototype Chariot rover. It was developed a number of years ago, and they built several prototypes. They also built a lightweight, super strong, basically a bulldozer blade, smoothing blade, and which they took it out to Moses Lake area and they pushed around a lot of dirt and it seemed to work out reasonably well. Here, for example, is the current column of the characteristics of the Chariot of the prototype was built, and then you can see the improvement required to get one that they would plan to use on the lunar surface. And of course, you want to add a microwave antenna system that can deliver enough energy. You notice there's two different sets of antennas. The smaller ones will operate at the higher frequencies for the sintering, and then later on we'll talk about resource extraction using lower frequencies to get deeper regolith penetration. And it's important, it's kind of a weird antenna design, but when you have a bunch of sources, RF sources adjacent, you get this standing wave pattern, which would create gaps in the heating. So the trick with this design is that in the transverse direction across the face of the array, you can minimize those nulls, those gaps, and there are gaps in the longitudinal pattern in the direction of travel, and those get dealt with as the vehicle moves forward. Here's a close-up of the antenna, and I didn't design this antenna, and I actually found the design in a paper written by an Australian. It was titled "Microwave Weed Killer." His problem was he was poisoning the soil with pesticides and herbicides rather, and so he wanted a way to kill the weeds without poisoning the soil, and so he developed this antenna, which had many of the desirable characteristics that for this application. And, I'm not the first person who thought about ways to sinter the ground with microwaves. This is one of the figures out of Larry Taylor's paper, called it a paving wagon. And he also believed that you could smooth the regolith and then heat it up enough with microwaves to melt it and to be effective. He referred to it as constructing a traffic-capable road. This is the results of some studies. Now, I could never find out to what extent the simulation of the regolith had been modified to try to reflect the presence of the nanophase iron particles, but this is what we've got. It's examples of regolith penetration studies for the various frequencies shown. And so you can see at 10 gigahertz, the energy is focused in the top layers, whereas at a lower frequency at 0.5 gigahertz, you get down a meter plus of heating, which is just what you want if you're going to try to heat up a lot of regolith and liberate volatiles. All right, surface radiation is another issue where sintering can contribute. Now, I think that lava tubes and other underground facilities are probably the best long-term option, but I think there's going to be other priorities on the early time on the lunar surface. And prefab habitats are heavy and cramped and obviously limited to the maximum, payload diameter of the launch vehicle. And so I think that it might be able to use an inflatable habitat. Other people have suggested that, but if you inflate it first, then you got a real problem trying to cover it with a reasonable amount of regolith. So my approach is to bury it first prior to inflation. Now you could start with something like this. This is an inflatable habitat that was jointly developed between NASA and the National Science Foundation. It got stored on 2 reasonable sized pallets and they flew it down to Antarctica, and they got it erected and operating down there. Although I read the final report and it said, to no one's surprise, that that getting it set up in Antarctica was significantly more difficult than it was in Delaware. But that they did succeed in getting it set up. All right, so this is the sequence that you would see if you wanted to do this technique of burying it first. You dig a 1.5 meters, 2 meters, maybe a little more trench as a foundation hole, and then you sinter the base to make a solid surface to put the bladder on, and then you deploy the bladder over that, and over that, the green line is a thick polyethylene sheet. Polyethylene is a wonderful radiation absorber, and it will also serve to protect the bladder of the inflatable from the glass shards, which in fact is what the regolith is made of. So you need some sort of protection. And then you fill it in and inflate it. And then, depending on the situation, you may want to sinter the low edges of the regolith pile to make sure to keep it in place when it gets close to the angle of repose. Obviously, there's no wind problems to deal with, but that's how you get it. That's how you get a regolith covered inflatable habitat. Now, you can also use microwave energy to harvest consumables. As I showed in the other chart, the low frequencies, about 0.5 gigahertz to 1 gigahertz, give you good regolith penetration. And what you need to do is cover the antenna, or perhaps the whole rover, with capture tent to collect the sublimate and then store it in a cold trap during the harvesting run before you return it for further processing. Now, here's a table showing the results of the L-Cross mission in 2009 that crashed a empty rocket stage into a shadowed crater, and then they measured the composition of what got blasted out. Lots of water, which everyone took as a really good sign for hopeful settlement. Also carbon monoxide and carbon dioxide, which is necessary. The carbon is necessary for a variety of things, not the least of which is making methane. And also of note, there's some ammonia in there, not much, but you can electrolyze the ammonia and get some nitrogen that'll be useful for cabin air diluent and a few other applications. And once you melt it out of the ground or volatilize it out of the ground, this is the kind of processing system that you'd need. You'd electrolyze the water in a solid electrolysis system, separate it out into the oxygen and the hydrogen, and then you take the hydrogen and you feed the carbon monoxide into it, and that will generate methane plus a lot of water, which you then return back to for further processing. It's as I mentioned yesterday, there is that one experiment where Larry Taylor took 80 grams of regolith and he heated it in an 1100 watt microwave oven, and he got a heating rate of 1,000 degrees a minute, which I guess is faster than your tea water would boil. So I try to calculate how if that's the heating rate you get, then I would scale that to the mass of the regolith that you'd be heating in a sintering run, and for the temperature change you need to get just below the melting point of the regolith. And from that I calculated that you might be able to sinter at a rate of up to about 1 kilometer an hour. It's going to take a lot of RF power, but I think that kind of level is possible. When you're trying to heat the regolith to harvest the volatiles, much bigger volume, but much smaller temperature change. And there's a lot of water that you can harvest in the course of a 12-hour collecting run. And just so no one thinks that this is a complete pipe dream, I made it like a bill of materials for the components that you need to do this system using just commercial parts, so I get a sense of the masses we were talking about and the energy requirements. The energy requirements turn out to be non-trivial. If you want to, turns out if you want to run for 12 hours straight just on battery power, you need think like 2 Tesla Model S plaid batteries, about 240 kilowatt hours. It's a lot, but it's not, it's not totally unreasonable. So here's the rough wag at what the mass and the dimensions of the power consumption of the system that I'm talking about. It would be on the rover. And you need some way to recharge the battery on the rover. And one possibility, which I think has some promise, is to get a couple of the new rollout solar panels that they've developed for the ISS, and you can just erect them vertically on the lunar surface and point them at the sun, which will be circling around the sky near the horizon. And they're not unreasonable in terms of size. The lower left picture shows a pair of them stowed in the unpressurized section of the Cargo Dragon capsule heading up to the space station. So, and each of them puts out about 20 kilowatts. So you could, in the time available, recharge, with a couple of those, you could recharge the system. Obviously, you couldn't recharge it at night, but there's plenty of preventative maintenance and other things to do if you don't have some non-solar power system. So, and then you could fit one of those things with the antenna and the bulldozer blade into a Starship. And so it would be possible to deploy one of these during the uncrewed flight test of the human landing system prior to Artemis 3. And be 3 or 4 metric tons and a package that would easily fit within a 9-meter payload fairing. And so I think it's possible to do something like this and then check it out. So that concludes my presentation. Take any questions folks might have.
Thank you, Carl, and right on time as well. Very good. We do have one question from James Sloan. Has any consideration been given to using mined iron to form the road?
I have not, but I mean, it's certainly a possibility.
Yeah. Would that be possible to combine with the microwave sintering, or would that be a different technology altogether, I wonder?
Well, I think it would be different in the sense that you'd need to collect the iron people were talking about yesterday in order to have it available. In this case, you just drive along and melt the ground in front of you. So
yeah, and this essentially use the iron that's already there. Yes. And there's a question from Aled Roberts. Could the microwave device have any other uses? I mean, you have 2 here, obviously, extracting and paving.
Well, the concept I had was that it would spend all of its time harvesting volatiles to collect the water and the carbon monoxide so that you could make rocket propellant. And because even at the rates that I calculated, which are probably reasonably optimistic, you still need about 6 months to refuel a Starship collecting it that way, and a lot of energy to do that process.
Yeah.
Has there been any studies about how durable a sintered regolith product would be, load bearing especially?
There have been, but it all uses simulants, and so there's that question. And also they tested samples, but it was in the context of, if we make what amounts to a cinder block, if we sinter like a cinder block of regolith, can we build a building out of these cinder blocks? And
right.
So I think they're talking about strength parameters, that are different than what happens when you just try to sinter it right on the ground.
Right. And do you know if there's been any studies doing like a trade analysis between microwave sintering and solar thermal?
I'm not aware of it. I know that there was a demonstration system that was built with a big solar concentrator that would go around and melt sand someplace, but I don't not aware of any comparison, attempt to
Okay.
compare the two.
Grace has a question. Can you control the inflation of the habitat such that the regolith slope of the edges doesn't exceed its angle of repose? We suggest. I think that's the correct term as well.
Yeah, I think you would design the bladder such that when it's inflated, it stays below the angle of repose, but of course, that has a non-trivial impact on the usable interior volume, because angle of repose probably in the 40-degree range, and so you got a lot of low slope, like a cheap apartment with the gables off on the side. But you design the bladder such that it would be up to, but not too far exceeding, and then you could decide whether you needed to sinter the edges.
I guess you could design it so that there are capture pieces that holds it up, so that you keep it on the roof, so to speak.
Yeah,
if you just had a little bit of it, that's true, but we're talking about 2 meters of regolith, so that would be, if you could, design the ribs into the top, so that, it would hold it in place, but that's asking a lot of what amounts to a flexible rib. One of the interesting downsides of this, inflatable habitats really sound great because you get a large volume, living volume on the surface for not too much launch volume. The calculation of how much gas you have to bring with you, to inflate it is it's non-trivial. The only good news is that you could use those tanks to store the propellant that you make, or drinking water, or whatever you want. And even COPV tanks at maximum reasonable pressures, you still need a lot of mass of nitrox to inflate those things.
And if you make it in situ materials, that will take a lot of microwave energy. Any other questions or comments? James Sloan has a suggestion. What about surrounding the habitat with an inflatable wall?
To retain the regolith? I'm not sure why you.
Well, wait, the way,
Yes.
yeah.
I suppose that's certainly possible.
I've seen designs where you have like a carport that you have your inflatable underneath, and then a rigid structure over that, and then you pile your regolith on top of that. But it seems like it makes it even more complicated.
Well, it certainly, an inflatable wall around the habitat would certainly help with the problem of the shallow angle. It would mitigate some of the disadvantages of the shallow angle. You could make the angle steeper and still have and to have more usable interior volume and still retain the regolith.
Do you know of any studies that have been done showing the vulnerability of inflatables when you put regolith directly on top of it? Because as we all know, that stuff's pretty darn sharp.
No, but that's where that polyethylene layer came from. But that's an unknown that would have to be dealt with.
Right. Because we know that the moon shakes quite a bit, and I just always envision you've got that regolith sitting on top of a fabric and it's shaking.
That's certainly something that would have to be, maybe a Kevlar layer also.
Right. So something that at least resist it somewhat. Yeah. Marufa's got a question. Is technical specs for microwave design similar to those that we use at home?
Well, yeah, it's it's pretty much the same thing. You'd have the energy sources, the RF sources would be around a kilowatt, but you'd have a lot more of them, and you get about 10 to 15 dB of antenna gain, so you get much more effective radiator power than you would have in a microwave oven, but the principle's certainly the same.
Cool.
Thank you. And I think that concludes this Q&A. Quite good questions, I think. Thank you, everybody asked.